Hello, ICP. We're going to be starting chapter 12, a little intro on what are forces. So I've got chapter 12 here in my notebook right after my gravity page. So this is the last thing I have in my notebook. A force, and we're going to use that same definition that you probably learned in elementary school, and that's okay because it's still valid. A force is a push or a pull. And it's not always felt. Earth's gravity is pulling on us right now, but we don't feel it actively pulling on us. So that's what I mean by it's not always felt. Forces can change motion, and sometimes they don't, because Earth's gravity is not causing us to move, it's just causing us to stay where we are on Earth, not floating up. They have direction, which means that they are vectors, and size or magnitude, because vectors have size and direction. Oops, direct. I started to write vector there, I think. I was thinking about vector. Have direction and size. The SI unit is going to be called a Newton. Newton, and we abbreviate it with a capital N. And it was named after Isaac Newton, and we're going to look at Newton's 3 laws of motion in this chapter. A Newton is actually a kilogram times meter per second squared. And when we get into the math part of it, we'll look at that more. But see, that's a fancy unit. These are all SI units. This is called a derived unit when we have more than one of our 7 base units. But together, instead of writing that over and over, we just call that a Newton. 2 main types of forces. I've got unbalanced forces here. When forces are unbalanced on an object, they can change the motion of the object. Unbalanced forces cause change. So I'm going to be doing some free body diagrams, and these are very simple. I'm not even going to get into all of the forces acting on them today. Usually we'll make a box. We do a lot of boxes, or sometimes they'll use little dots for the diagrams, but for us, we are going to use some boxes because it'll keep our numbers more organized. So I have this object, this box, and I'm pushing on it. Regardless of whether or not I'm pushing or pulling on a force diagram, the arrows are always moving out. Got someone using 5 newtons to pull on it, and then someone using 7 newtons of force. The arrows, this one's larger, because the force is actually larger. What I said that we're going to be skipping some other forces because technically we're going to have the normal force, which is this one, and then the force of gravity acting on them, but I'm ignoring them right now. And then sometimes we'll have friction after I introduced it, but we're going to assume that there's no friction, so we just have these two. When forces are acting in the same direction, we're going to add them. And this was like with our displacement. If you kept going in the same direction, you could just add that together. So same direction, we can add. So with these vectors, to get the overall net force, so the net force is the overall, like once you balance and cancel everything out, I'll add these together. 5 newtons plus 7 newtons equals 12 newtons. And then we draw an arrow to show the direction that that force is going. Since these are both going towards the right, I drew an arrow to the right. Let's look at my next example of an unbalanced force. These two forces are going to act in opposite directions. I'm pulling with 7 newtons to the right, and we'll pull with 5 newtons to the left. When forces are acting in opposite directions, guess what we do? Just like our displacement, we're going to then subtract these. So these are acting in the exact same direction or 180 degrees apart. So my net force And we'll do the larger one minus the smaller one. So the net force on this is going to be equal to 2 newtons. And then we draw an arrow in the direction of the larger force. So the overall force will be going 2 newtons that way because we cancel out 5 newtons over there. Put that arrow on there. It's a vector. It has direction. Now, if these are at a 30-degree angle or a 60-degree angle, you would have to use trigonometry to figure out the force vectors in which direction. And that would be a higher level physics class. And our last example are going to be balanced forces. Balanced forces, the net force ends up equaling 0. They're balanced. They end up being equal, and they do not change the motion. Do not change motion. For example, if my box is just sitting on the ground, its weight is going to pull down. Gravity is pulling down on that object, and that's a force. So we get the force of gravity acting down. Well, the tiles that this box is sitting on are preventing it from crashing to the center of Earth. So the tiles are pushing back with a force of 540. Since these two are in opposite directions, you would subtract them. And then see that they cancel out. They balance each other like a seesaw, that you have a teeter-totter, that you have perfectly balanced. And this one I didn't put any forces on from the left or the right. So the net force here is 0. 0 newtons.